Okay, so in our case, we're now going to enable segment routing. So what we need to do first globally is turn segment routing on and then advertise the prefix SID, the connected prefix SID map, which again effectively is advertising your loopback. Okay, but let's take a look at where do you find this in the documentation. Okay, so from the main documentation, and actually I'm going to skip this. Let's just Google this because we need to just jump to the iOS XE and the iOS XR config guides. Let's say OSPF segment routing, which is this. No. I'm looking for this one here. Okay, so ASR 1000. And then we want segment routing with OSPF version 2 node SID. Okay, what this means is it's fancy terminology to say you're advertising your loopback into segment routing. The node SID is your loopback. Same as you did in regular MPLS, that you had to make sure to advertise the loopback with a label because that's what the next hop is for the VPN version 4 or the VPN version 6 route. Okay, same is true for the layer 2 VPN. Your pseudo wire is coming from your loopback. So unless you have a label, unless you have a label for the loopback, the transport label, I should say, then your pseudo wire label is not going to work as well. So it's both a layer 2 VPN problem and a layer 3 VPN problem. Okay, so we want to see how to configure segment routing with OSPF v2. So what do we need to do? Configure segment routing with OSPF. Configure the prefix SID. Okay, it used to show which were required steps and which were optional, but most of these are optional. Okay, the only thing that we really need to do is to turn segment routing on, go under this map, and then advertise our loopback. Okay, second step is to enable segment routing on the OSPF network. This is under the OSPF process. Say segment routing, then segment routing for the particular area. Okay, so let's open up router 1. And globally, we're going to have now segment routing. Okay, under segment routing mode, we have our connected prefix SID map. Address family is IPv4. Okay, notice in this code version, IPv6 is not yet supported. And our prefix is 1111/32. Okay, two options here. We could give an absolute value. Absolute value would be like 16001. Or we could say, what is the index number? The index is just 1. Okay, so that would be 16,000, which is the start of the sRGB, the segment routing global block. It's adding 1. It means its label is 16,001 for this particular prefix. Okay, so do show run section segment. Okay, so we're now advertising the prefix SID. The second portion is under OSPF. The router OSPF 1, segment routing MPLS, segment routing area 0 MPLS. So let's do show run section OSPF. Here we have router OSPF 1, segment routing MPLS. Segment routing area is area 0. Show run section segment. Okay, so not a ton of config. Okay, let's go ahead and replicate this on the rest of the regular iOS boxes. So router 2 is going to be 2222. Its index is 2. And likewise, under OSPF, it's running segment routing. Okay, then on router 3, 3333, index value is 3. Okay, if we show IP OSPF segment routing, we should see segment routing is globally enabled. We have segment routing enabled for area 0, and we're preferring LDP over segment routing. So again, this means that if you're running both of them at the same time, and you have a label for the same prefix, one through LDP, one through segment routing, then you're going to prefer the LDP path. This again is the way that you can do a brownfield migration, meaning that the network is already running. You don't want to take an outage, you don't want to schedule a maintenance window, you just want to gracefully migrate this in. This can be accomplished with segment routing and LDP at the same time. Okay, so let's see what is the result of this now. If we show MPLS forwarding table, we have a label to get to router 1 that is 16,001. Okay, to get to router 2, we would use 16,002, but we are connected to them, so we would pop whatever the top label is as it's going out towards that destination. Notice in addition to this, it's specifying we have labels for the adjacencies. So we have a label for the adjacency between router 3 and XR3. We have one between router 2 and 3, one between 3 and 12. Now if we map this back to the topology, this is from router 3's point of view. It has 3 adjacency SIDs that it is generating. So it has a label for this link to 2. It has a label for this link to XR2. It has a label for this link to XR3. Okay, these ones aren't going to be used though until we're programming something with traffic engineering. Okay, so let's go ahead and do the same thing with the iOS XR boxes. So let's search segment routing, iOS XR. And this is the config guide for Cisco ASR 9K. Now, if you look at the newer versions for this, I believe 6.5 is maybe the current version. There is SR IPv6 support in the newest code, but this version is not yet ported to viral. So hopefully, I don't know, maybe 3 months, 6 months, there's a new version update, then we would be able to test those new features. Okay, in the meantime, it says, how do you do this on iOS XR? Well, the first thing we need to do is enable segment routing for OSPF and then configure the prefix SID. Okay, so same as before as we saw in regular iOS effectively. So under the OSPF process, run segment routing. We specify we're running it for area 0. MPLS traffic engineering, we'll talk about a little bit later. You don't necessarily need to do this, but you probably would want to. Just you're prepping the routers in advance that if you're going to run traffic engineering down the road, then they need to have it enabled both globally and on each of the interfaces. The change though is that you don't need RSVP because segment routing basically replaces the functionality of RSVP-TE. Okay, so in our case, we have router OSPF 1. We have segment-routing MPLS, and actually let's just do live. Let's just do this live. So let's go to XR1. Okay, so let's show run router OSPF. So this is under OSPF process 1. We have segment routing MPLS. Under area 0, we have segment routing MPLS. Then we have our interface, which is going to be loopback 0. And this is the second portion where we're configuring the prefix SID map. Okay, so under OSPF, under the area, under the interface, what is the prefix segment ID? Prefix SID. Prefix SID is going to be an index, and this is node 11. Okay, so really not that involved here. Okay, XR2 and 3, they're going to do the same thing, but we're going to have different prefix SID indexes. So we say router OSPF1, segment routing, Area 0 has segment routing. The loopback is label number 16,012. Okay, same thing on XR3. Index is 13, meaning its label value is 16,013. Okay, so next let's go back to router 1 and look at the show MPLS forwarding table. Okay, notice that we see the labels for the loopbacks. We see some of the transit interfaces, but notice which ones are these from router 1's point of view. 10.1.12, 10.1.11, 10.1.2. All of these are the three interfaces that are going from 1 up to 11, 1 to 12, and then 1 to 2. So it has three adjacency SIDs, or segment IDs, and then it has these node segment IDs that correspond to router 2, router 3, XR1, XR2, and XR3. So the point being is that since we don't even need those labels for the transit links, segment routing by design is a little bit more efficient than LDP because we're not advertising all of those labels. Now, down the road, assuming that you want to use traffic engineering and do some sort of link or node protection, you may need to know what label values are associated with the links themselves. So 42, 43, and 44. This is what the SDN controller would do, that you advertise this out to them with a protocol that's called the Path Computation Element Protocol, and it calls the controller the Path Computation Element. So this is, right now, this is pretty much just a logical construct that they have not yet implemented. But in later versions of the code, this is built into XRV itself. So you could use the router for this, or there's an application, I can't remember the name of it offhand, but there is an application that Cisco has to export this traffic to. It does the calculation offline, and then it pushes the labels back in to say, hey, I want you to go this particular way when you're routing the traffic from A to B. Okay, from our point of view right now, though, the end final result is that there's not a functional difference from the customer's point of view. They just see the transport as working. Okay, additionally, let's go ahead and do a trace route. Trace to 7 from 6. And notice here what label value that we're using. The final destination out of the provider network is router 3 in our particular case. Okay, we're going from 6 to 5 to 1, 1 to 2, 1 to 3, and then out. When the IP packet is encapsulated inside of MPLS, what normally would happen is that there would be two labels pushed by router 1. Okay, it would have the LDP label, and then it would have the VPN label. It forwards this to router 2, then router 2 would swap the labels. So it would take whatever LDP label is coming in, and then, or actually no, in this case it would be popping it because it's the penultimate hop. It would delete the LDP label and then forward it on with just the VPN label. But notice what happens in this case. We have router 3's segment ID that's being used here. So when 1 is doing the imposition, and let's actually make this a little bit easier to see, but we're going to go to router 3 and we're going to shut down the connected link to router 2. Okay, we're going to make it go a couple additional hops. So between 2 and 3, let's say interface gig 2.12 is shut down. Okay, same thing on router 3. Gig 2.23 is shut down. Actually, what did I say on 2? No, wrong one. Gig 2.23 shut. Okay, now let's see. Can the customer reach across? Yes. Okay, which label is it using now? So let's do a trace route again. So from, it's going 5 to 1 to 12 to 3. Okay, so let's take out this link as well. I'm trying to get it to go 2 or more hops before it does the penultimate hopping. That's going to make this a little bit easier to see how these global labels are working. So on XR2, we want to say interface gig 0000.312 is shut. Gig 0000.312 is shut down. Commit. And then on router 3, gig 2.312. Okay, so let's try this again. Can we still reach them? Yes. When we trace, now we see the difference. Okay, the key here is that label value 16,003 shows up twice. So instead of LDP swapping the labels that are locally significant on a hop-by-hop basis, router 3 is telling the rest of the OSPF network that, hey, if you guys want to get to my node, use the global block, which is 16,000, use the index number 3, so add the two together, 16,003, impose that, and then forward the traffic towards me. Now, where this starts to come in with traffic engineering is that if we wanted to say, I want you to use the link between router 2 and XR3, what that would look like would be 16,002, and then whatever the adjacency SID is between router 2 and XR3, then followed by the VPN label. So we would, and then under that 16,003, okay, which is the final PE. So it says get to the node router 2. Use that link for the particular adjacency. Then get to the node router 3, and then at router 3, the VPN label would be 18. The key point, though, is that this can be signaled by the source as opposed to having to use an MPLS traffic engineering tunnel. So you can do regular TE, and we'll look at that later, how specifically that works. But the idea of this overall is that going forward, you're going to have an SDN controller that's making these decisions. So it has all of the node SIDs, it has all of the adjacency SIDs, and then it can dynamically push this back into the network by saying, hey, I want to get low latency. Low latency is tagged on these particular links. These are the node IDs plus the segment IDs that you have to particularly use.